Okay, second example, finding the area of an enclosed region, but this time we're going to have to go right curve minus left curve. Let's see what the difference is here. You may be curious, why can't I always do it the way you initially showed? So here's a warning before we begin. This is an example that requires a dy. And you can remember this. If you're integrating and you've got this thing tagged with a dy, your integrand must be written in terms of y. The only variable in your integrand is a y. So make sure you're not combining x's or u's within a dy integral. It can help keep you straight with what you need to know. And we'll get with the example. Here comes one example where we're going to have to go the right curve minus the left curve. I kind of think in my own brain about a top curve minus a bottom curve, and the top curve is the higher curve, the higher numbered curve. Well, if you're moving left to right on a number line, it should make sense to you that the right curve is the higher number than the left curve. So going right curve minus left curve perhaps makes some intuitive sense in that regard. Let me show you the curves we're talking about here. We have y equals x squared, just our standard parent function quadratic parabola. We have an inverse function, y equals 8 over x. And lastly, the horizontal line, y equals 1. This is a horizontal line that passes through the y-axis at the coordinate 0, 1. So if we see this graph, we'll see a graph that encloses a region. And the intersection of points, I've got 2 out of 3 of them here, and you can see the highest intersection of points is the order pair 2, 4, and the lower left point of intersection is the order pair 1, 1, and pretty clear to see that there's an intersection point of 8, 1 there far right. But we'll use these 2 points only. Will allow us to find our limits of integration for this problem. Let's look closely at the graph. And you can see the enclosed region. And the problem with integrating top curve minus bottom curve is as we move from left to right, if you can picture yourself inside that region moving from left to right, the top curve connecting that vertical green line, which is hitting the top curve and the bottom curve, you'll notice as you move from left to right, the top curve changes. The top curve changes. This is what disallows us to use dx. It disallows us from going top curve minus bottom curve. You may be wondering initially, can I break this up and just do 2 problems and add them together? The answer is yes, but you'll find further that you're really going to make life easier if you choose to go right curve minus left curve on a problem like this. And you'll kind of be expected to do so, like the multiple choice selections to make. Like it'll ask for your integration setup. Well, your integration setup, they're expecting that you know how to set it up with regard to right curve minus left curve. So you see a scenario like this, please get used to setting up going right curve minus left curve. Top curve minus bottom curve is just a scenario that's going to cause you difficulty that we want to stay away from. Let's see what happens here if we set this up going right curve minus left curve with a dy. See the dy tagged at the end. So that is important. Here is our graph. Here are our 3 equations. Now, since we are integrating with respect to y, as I had made mention earlier, now we're thinking of each rectangle, kind of stacking these rectangles from low to high. I think about stacking them like pancakes from low to high. Each rectangle has an infinitesimally small width, very, very small difference in y's, right? So we kind of understand that picture. we have to reformat our functions. We have to write each one in terms of y. Remember, our integrand is going to be written in terms of y. Right now, our three functions are written in terms of x. So really what we're doing here is isolating the x and solving for the x so that we have written the first function now in terms of y. We took the square root of both sides to isolate the x, and we get x equals root y. We get x equals 8 over y. And the parabola, I'm not so concerned about having the plus or minus there. You can see I'm not using the minus side of the parabola that opens upward there, so we're fine. X equals root y and x equals 8 over y. Why didn't you do anything with the y equals 1? Well, you'll see how the y equals 1 is utilized in the problem, but not utilized as part of the integrand. Stay tuned. So again, we're looking at this graph. We've got our two functions that we're going to use, and this time, in order to find the area, in picturing this, we're going to kind of stack pancakes. Looks like this. So now we've got the whole area filled up, and we're stacking from low to high. And so in this case, with our ordered pairs, it won't surprise you that we're not stealing the x's in the lines of intersection. We're stealing the y coordinates. So we are integrating from as low as 1 to as high as 4. So remember, boy, when you're writing a dy, three things need to occur to you. And if you fall off the ladder in one of these three areas, your entire problem is going to be wrong. Your limits of integration got to be y's. Your integrand has got to be written in terms of y. And you got to have a dy tagged at the end. Three things. You got to remind yourself of those three things. Important. You know, like I said, you botch one of those and your whole game is done. So you can see here we're integrating from y equals 1 to y equals 4. And we're going to go the right curve minus the left curve. So we identify each. The right curve is the function 8 over y, while the left curve is the function root y. So we set up our integration that way. We're integrating from low to high, from 1 to 4. The curve on the right, which is 8 over y, minus the curve on the left, which is root y, dy. All three points of emphasis there. The limits of integration, the integrand, and the dy all have to align. And so you've done the tough work. Now you've got really an elementary integration problem in front of you. Let's see if we can handle this. I've just rewritten the square root of y as y to the 1/2 power so that we can then use the power rule in reverse. And I want to add 1 to the exponent, divide by the new exponent when I get there. When I integrate 8 over y, that's like 8 times 1 over y. You may wish to think of it that way and factoring out that 8. Anyway, I've got an 8 in front as a multiplier. 8 times natural log absolute y minus 2/3 y to the 3/2. We've reached a point now where we know how to add 1 to the exponent of 1/2 and then dividing by that new exponent, which I understand is dividing by 3/2, but dividing by a fraction, the same as multiplying by that reciprocal. That's from where the 2/3 arrives. And we still have to evaluate this from 1 to 4. So we're using FTC1 now. We're plugging in a 4 wherever we see a y, minus we're plugging in a 1 wherever we see a y. There's the plugging in of a 4 at the two locations where we see a y, minus now plugging in a 1 at the two locations where we see a y. So this first expression is going to be 8 natural log 4 minus 2/3. Let's see. 4 raised to the 3/2 bothers some students. So picture that as 4 to the 1/2 power, or the square root of 4, which I know is 2. And now go 2 cubed, which is 8. So that's how we arrive at that 8. Think of that 3/2 as broken down into a 1/2 power cubed. So again, 4 square root of 4 is 2, and 2 cubed is 8. In the right set of parentheses, we have to be at a point now where we recognize that the natural log of 1 is 0. So I've included that. And when you put a 1 in and raise it to the 3/2 power, 1 to the 3/2 power is 1. And 1 times 2/3 remains 2/3. So continuing on here, getting 8 natural log 4 minus 16/3. Subtracting a negative there at the end is plus 2/3. Your final answer here is going to be 8 natural log 4 minus 14/3 units squared. That's the area of the region. So on an AP exam, that's the multiple choice selection that you would be looking for when you're trying to find an exact answer. That's the one that you will likely see in that format. So I had to be able to find a numerical value of some numbers raised to a fractional exponent, and also gotta have and understand a couple points on the natural log function, like the natural log of 1 here, super important, and 2 points on that natural log function and 2 points on that e to the x function will prove to be very important. You ought to be able to kick those out without any trouble. So you've seen one example here of taking the top curve minus the bottom curve. This example, a right curve minus a left curve, and the limits of integration are y's. The integrand is written in terms of y, and of course I'm integrating with a dy. Those are the 2 types of challenges you will get, and that kind of is the nuts and bolts of finding the area of enclosed regions. When you get multiple regions, you just find the area of one and then find the area of the other. Just realize that when you have 2 regions, sometimes that top and bottom curve might swap up, and the right and left curve might swap positions as they intersect and form a second region. So just a heads up on your way to solving some additional problems that are a little more complex. Hope you're sitting pretty. We'll talk to you soon. Calculus Made Easy. Finding the region area. Right curve minus left curve. Over and out.